Welcome back. In the last short video, I tried to give a quick description and definition of what parametric equations are and a couple examples of how to graph them really by hand. And one quick example of writing an equation in parametric form. Keep in mind that you should play with the calculator a little bit and try to figure out how to graph the two that I gave you on the calculator and see what it looks like. Play around with the step, especially for the parameter, and see what it might look like. Here I want to focus on eliminating the parameter. And what that means is we're going to have a system of parametric equations. By eliminating the parameter, we want to turn it into our standard rectangular form. So if you see that phrase or word rectangular, that's all it means, our normal x versus y function. So in order to eliminate a parameter, this is actually an example from the first video, we basically just use a substitution. Now I know there were requirements and restrictions for t, but it really comes down to this. I know that if I can just solve the system of equations by solving for t and then substituting, I'm in pretty good shape. So I can look at this any way I'd like, but here I can solve for t very easily. T is just going to be y over 2. So now we substitute y over 2 here. We get x to be 3 times y over 2 squared, which would be x equals basically 3/4 y squared. We just studied conics. We know that's a parabola. We know it's a sideways parabola, and we may know a lot about it. We know its center. We could find out all of the other stuff if we wanted to. We would just have to put the 3/4 on the other side so it fits the general format. But it is one of our conics. But that's what we mean by eliminating the parameter. Now, I will say this. Because the original one only went from -2 to 2, we would have to somehow restrict these x values, or the y values. In this case, y would only go from -4 to 4 if we just get that little section. On this next one, it's a little bit trickier, because if I want to try to solve for theta and then use more an algebraic-minded approach, I would end up with theta either be the inverse sine or inverse cosine. And I don't want to put a sine of the inverse cosine or a cosine of the inverse sine. I can deal with it. We've done it in the past, but we don't need to. What I'm going to do here is make use of one of our most basic identities from all of trig, and that is the Pythagorean. Sine squared plus cosine squared equals 1. So in this case, I'm going to realize that sine of theta is simply x over 2, and then cosine of theta is going to be y over 3. Now I know that sine squared of theta plus cosine squared of theta equals 1. So now I'm just going to make a substitution. That's going to be x squared over 4 plus y squared over 9 equals 1. And we know what that is. That's an ellipse. The center of the ellipse is 0, 0. The major axis is vertical. So we go up 3 and down 3 to get the endpoints of the major axis. Because of this 4, we go left and right 2 to get the endpoints of the minor axis. We could find the foci if we wanted, but that's not really the point. So if you had to graph this function, it might be helpful to actually write it this way, or vice versa. If you had to graph this function in your calculator, you could write it this way and use the parametric mode, rather than the rectangular mode or the function mode and have to solve for y and have a plus or minus. So a lot going on here. Just trying to give you options for future courses. Now, this next piece, we get into some physics. And we've already seen that several times throughout this course, whether it was working with law of sines, law of cosines, working with simple right triangles, moving into some of our vectors, we've discussed some physics, because mathematics and physics, especially the trigonometry, go together very well. So what we're trying to do here is talk about certain types of motion. And it's called projectile motion. It's a very simple idea. A projectile is anything that might be shot, kicked, thrown up into the air. It could be shot, thrown, or kicked at a certain velocity, at a certain angle, And based on the velocity and the angle, we can know how far it's going to go, how high it's going to go, how long it's in the air, all of those types of things. But rule number one to all of this in terms of the physics is that the horizontal movement and the vertical move, other way around, the vertical movement and the horizontal movement are totally separate. They're separate components. So what's happening to the height of a function is really not being affected by what's happening to how far it might be traveling, except when it finally hits the ground and stops. So what we have is the ability to write projectile motion in terms of not so much a single function, but as a set of parametrics, where this is the horizontal. So in other words, where it is, the projectile, based on where it started, is a function of its velocity and the cosine of the angle and how long it happens to be in the air. That will tell us how far something is. Now, vertically, you might just remember this as the free fall formula, which we've studied. Now, this gravity could change from either negative 32 or negative 9.8, depending on the situation. Because of this negative, it's actually going to end up being positive. But here we have the components that would give us the height at any time. This h, of course, being the initial height. Now, why a lot of this happens is simply because of, let's just take a look at the little triangle. Okay, if this is kind of the angle, and this is some velocity, if we think about why all of this works, is this is my vertical component, and all of this is my horizontal component. And let's think about how long this is. We could call this x. Well, of course, I could simply say that the cosine of theta is the adjacent over the hypotenuse. And then if I solve for x, I get cosine theta times v sub 0. So that's kind of the one unit. But then if it's in the air for a certain amount of time, that's going to be telling me how far this thing is going. So let's set up with, and by the way, the next part would be the same thing. We'd have to figure out that, right? But that's a free fall problem based on gravity and the initial height. So here's the situation. We have a golf ball, and it's hit with an initial velocity of 100 feet per second at an angle of 30 degrees with the horizontal or the horizon, right? So it's not too high, not too low. We want to write the parametric equation that fits this situation. Well, it's really going to be as simple as realizing this is 100, this is 30 degrees, and we get t. Whereas y is going to be, it's in feet per second, so we'll get negative 16 t squared plus 100 make a little change on that. Hopefully you notice that. Sorry. That has to be sine, of course. So it's going to be the sine of 30 plus the initial height, but that's just going to be 0 because the golf ball, we would assume that it's hit from the ground. Okay? So there's our parametrics. Now we could go a little further with this. I could simply make this x equals the cosine of 30, I think, is radical 3 over 2. Is that right? Yeah. So it's going to be 50 radical 3 times t. Whereas the y is going to be negative 16t squared plus sine of 30 is just going to be 1/2. So I get 50t. So now I'm not even going to complete the rest of this example. I just might talk through a few of the key points. And I believe this is in the textbook. But once we have this system of parametric equations, I could ask a variety of problems. I could find out how far is it after 1 second, or 2 seconds, or 3 seconds. I could also ask how high is it after 1 second, or 2 seconds, or 3 seconds. But there could be some more interesting things. I could find out what's the highest it can be. Well, the highest it can be is basically when this height, it's basically going to be the vertex of that parabola. I could find out how long is it in the air. Well, if I want to find out how long it's in the air, I would have to let this be 0. Because I know when time is 0, it's on the ground. When else is it going to be on the ground? So I would let the height be 0. I could ask, how far did the ball go? Well, I would first have to find out how long it's in the air, and let's just say it's in the air for 3 seconds. So then I would put a 3 into x, and that would tell me where is it at after those 3 seconds. So because of these two parametrics, there are many questions I can answer, but I have to remember that these are not, one really doesn't affect the other. But the question that might be phrased in B, C, or D might use both of them, but not at the same time. So that's what we have with parametric equations. Work through the problem set from 11.7. As I said, this is basically the last lesson. I will have kind of a couple review videos next week, but what we really have to prepare for now is a worksheet, which will be a homework component. That'll be posted early next week. Middle of next week, a final test over all of these conics, more of a quiz than a test, almost like the last one we had, and then ultimately prepare for an exam. So we're getting close. If you have any questions or concerns, please don't hesitate to send me a message, and hopefully can take care of your questions either through email. I can post something on Schoology, or I can even have a short little video. But enjoy your day and actually your weekend, because I won't be back until next Monday. And good luck.